Okay. All right, so try these examples and let's see what you come up with. Wow, that was 15 minutes ago that you reminded me. Please, please, I don't mind you talking. So if it's something important, like you noticed that I wasn't recording, please, speak up, please. Okay. All right, so let's see what you come up with. All right. So let's see what we have here. We're going to apply the definition, right? So first one simply says, take your absolute value, the contents of your absolute value, which happens to be x minus 3, according to the definition for less than, you're going to place that between -7 and 7, and then solve for x. So I can solve for x by adding 7 on all three sides. cancels out. X is between -4 and 10, all right? So my interval notation would look like this. X is such that X is between -4 and 10. My set notation, I'm sorry, my interval notation would look like this. Notice that I'm using parentheses this time instead of brackets because there's no equal to here. If there were, then I'll use brackets. But since it's strictly less than, I'm going to use parentheses. Okay. And then you do the same thing for the second one. The definition here says, take the contents of the parentheses and make it less than whatever number is here. So I take the numbers between these two bars, which is x minus 3, and I make it less than -7. Or x minus 3, and this time make it greater than the positive of the number, so greater than 7. And then solve for x in each case. +3 plus 3, x is less than -4, or +3 plus 3, x is greater than 10. So your set and interval notations would look like this. Set notation. X is such that x is less than -4, or union. X is greater than 10. Now we go to our interval notation. We start from -infinity all the way through -4, union 10 to infinity. Okay, so that's the extra thing I wanted to do in chapter 7. Okay, we're done with chapter 8 and we're moving on to chapter 9. In chapter 9, we're going to talk about systems of equations. Systems of equations. It's actually a pretty interesting topic. And we're going to get to do some application problems. We're going to do some mixture problems, which we were supposed to do in a previous chapter, but I thought it would be more appropriate to do it in this chapter. So you would have more tools available to do those type of word problems, okay? So let's talk about, systems of equations. Systems of equations, chapter 9. Systems of equations, all right? What is a system of equations? Well, a system of equations would look like this, right? So specifically, this is a system of two equations and two variables. Sometimes you can have a system of three equations and three variables, okay? Now, The solution to a system of two equations, two linear equations, and two variables. The solution is an ordered pair, x, y, that satisfies both equations in the system. What does that mean? All this means is, if I were to pose the following question, if I pose the question like this, is 1, 4 a solution to the system? Is the ordered pair 1, 4, is it a solution to the system above? In order for me to claim that the ordered pair 1, 4 is a solution, that ordered pair 1, 4 must satisfy both equations in the system, where satisfying means that when I plug in x for 1 and y for 4, it should check out. I should get the same answer on both sides, right? So if I were to do that, if I were to say, okay, now I'm going to check, I'm going to plug in 1, 4. Let's call this equation 1. Oops. Why does this happen? Okay. Let's call this equation 1. And let's call this equation 2. Whenever we do systems of equations, we're going to label the equations. And we're going to label them with Roman numerals because, I mean, the problem already has enough numbers in it, right? I don't want to call it equation 1, like an actual 1 or a 2. And then when I'm doing my calculation, I might not be paying attention. And then I get the labels of the equations mixed in with the actual numbers in the problem. Okay, so I use Roman numerals so that that doesn't happen. All right, so when I plug in my 1, 4 for x and y in equation 1, so let's do equation 1. X is 1, y is 4, equal 5. 5 equal 5. It checks out. That's what I mean. It checks out. You get same number on both sides. Let's do it for the next one, equation 2. X is 1, y is 4. 2 plus 12 equals 6. 14 equals 6. Well, 14 is not equal to 6. If the ordered pair does not satisfy both equations in the system, then the answer is no. 1, 4. Okay. This pen is going crazy. Okay. Let me write here. The answer is no. 1, 4 is not a solution. If it were, it would check out for both equations. But if it checks out for only one of them or neither of them, then it's not a solution. So when I give you a system of equations and I give you an ordered pair and ask you, is this ordered pair a solution to the system? All you have to do is plug it into both of them. If it checks out for both of them, it is a solution. Otherwise, it's not a solution. All right. So here's one for you to try. Here's one for you to try. And I hope you're actually going to try it, because I'm going to ask this time around. Is -1 to a solution to the system x plus 2y equal 3, 2x minus y equals 0. So plug the numbers in and tell me whether or not this ordered pair is a solution to the system. I'll give you 1 minute to do that. So what did you get? Is it a solution or is it not a solution?
Not a
Anybody?
solution. Not a solution.
It's not?
Not a solution.
Okay. Okay, so let's check. X is -1 and y is 2. So I'm going to do it for equation 1. X is -1, so that's -1 plus 2 times 2 equal 3. -1 plus 4 equal 3. 3 equal 3. That checks out. The first one checks out. Let's look at the second one. So for the second one, equation 2, we have 2 times -1 minus 2 equal 0. -2 equals 0. -4 equals 0. This is false. So the conclusion is not a solution. Excellent. Okay. So we know what's going on here, and we understand how to determine whether or not an ordered pair is a solution to a system of equations. But then what if you have the actual system of equations and you need to find a solution to it, right? That's what we want to do next. We know how to verify whether or not a solution or an ordered pair, excuse me, is a solution to a system. But what if you're just given the system and asked you to find a solution? How do you do that? Okay. So now we're talking about solving systems of equations. We're going to use two methods. The first method they call elimination. The second method is called substitution. Okay, so there are two methods, substitution and elimination. When you do the homework, it's going to ask you to do substitution sometimes. Sometimes it's going to ask you to do elimination. Sometimes the software is going to force you to do one of the methods by doing the problem, like some of the problems in WebAssign, it asks you to go step by step. Like when you're solving an equation, it would say subtract 3 from both sides, and then do this and add 4 and so on, right? So I'm saying this to make the point that once I do the two methods, you can go with whichever method is easier for you, but you need to know both of them, because sometimes you have to use one of the other or the other. Okay, it's really an issue of preference, but there are times when you have to use one particular method. Okay, so definitely you should know how to do both methods. So let's start with substitution, the substitution method for solving systems of equations. Okay, the substitution method. So somebody sent me another message. I hope I'm recording. Oh, okay. Yeah. I remember you told me about your wisdom tooth. Somebody sent me a message about a wisdom tooth. So yeah. Um, David, to answer your question, uh, yes, you need to go back and click on the assignment. If it lets you, I don't know if that setting in WebAssign works. I didn't design the software, so I can only do so much. But if it allows you to only redo the ones you got wrong, then go in and do that. I tried to change the settings, but I don't know if that's possible. So click on it, or I don't know if somebody else has tried already. If you have, let me know. Have you tried doing the homework multiple times? If you have, did it make you do the whole thing over again? Or did it allow you to just redo the ones you got incorrect? Anybody? Homework? No? Okay. Well, you would have to do it to find out. Okay. Unfortunately, I cannot do homework. I can't do homework because the 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 version that I have is an instructor version, so it doesn't allow me to pretend like I'm doing homework. I could log in as a student and see the platform the way you see it, but I don't think I can click on the homework. So you would have to do it and let me know how it works. Okay. All right. And I would imagine that there should be, I would have to call them and find out, but sometimes if they don't have that settings, they don't. But try it and let's see what happens. And I'll call them today or tomorrow, whenever you give me feedback, I'll call them and see if they can do anything about it. All right. Because I do agree that redoing 40, that's ridiculous, right? You wouldn't want to redo all those problems. Okay. So just click on it and let's see what happens. And then we'll take it from there. So give me some feedback. If anybody, apart from David, if anybody tries to do the homework a second time, let me know what happens. Okay. So back to systems of equations. I want to show you the substitution method first, okay? So here's an example. Solve x plus y equal 3. 2x plus 3y equal 8. Okay. Now, I want to solve this system of equations using the method called substitution. First thing I do is to label my equations. I'm always going to label the equations. Equation 1, equation 2. I wish I could make this thing a little smaller. Can I do that? Yeah, I mean, taking too much space. Okay. So now we have the equations labeled. The next thing I'm going to do is I'm going to pick an equation. I have two choices. I'm going to pick an equation and solve for a variable, whichever one tickles my fancy, right? It doesn't matter. So two different people might approach it differently. Okay, so I could say, oh, well, I'm going to go with equation 1 and I'm going to solve for y. Another person would say, I'm going to go with equation 1 and I'll solve for x. Another person would say, I'm going to go with equation 2 and solve for y. But why would you want to do that when equation 1 looks so easy? Why would you want to go and start dividing both sides by 2 and 3 and so on, right? So in step 2, I am choosing to go with equation 1, solve for x. This is just my preference. So x plus y equal 3. Subtract y from both sides. Now I have x equal 3 minus y. So that's my first step. Now, once I complete step 1, in step 2, I'm going to take whatever I got in step 1, the results that I got in step 1, and plug it into the other equation, the unused equation. There are two equations. I chose one to do something with it. Now there's another equation that I haven't touched. I'm going to plug the answer in step 1 to the equation that I haven't touched yet, which is equation 2. So I'm going to plug x equal 3 minus y into the unused equation, which is equation 2. Okay? So now 2x plus 3y equal 8 now becomes, I'm replacing x with this, okay? Why am I replacing it? Because if I'm going to claim that x is equivalent to this, then I should be able to use 3 minus y in place of x, if indeed they are equal. So I'm going to replace this with 3 minus y plus 3y equal 8. So I simply went to the other equation and replaced my x with the solution from step 1, okay? Now, 2 times 3 minus y plus 3y equal 8. Distribute. 6 minus 2y plus 3y equal 8. 6 plus y equal 8. Remember, minus 2y plus 3y is y. Subtract 6 from both sides, y equal 2. Okay, the goal is to solve for x and y. I just solved for y. Step 2. Step 3. Take your answer from step 2 and plug it into either of the two equations you started with. Either equation 1 or equation 2. Now you have a choice again, right? In step 3, I'm going to take my results from step 2 and plug it into either equation 1 or equation 2. Obviously, I'm always going to choose the equation that's easier to work with. I'm not going to go to equation 2 when I know equation 1 looks so lovely. So I'm simply going to say in step 3, I'm simply going to say plug answer from step 2, which is y equal 2, into either equation 1 or equation 2. Using equation 1, I have x plus y equal 3 becomes x plus y, okay, becomes x plus 2 equal 3. Subtract 2 from both sides, x equal 1. So we just solved the problem. The solution is 1, 2. That's the solution. Substitution. That's the method, substitution. When you do the homework, you're going to see problems, substitution problems that look much easier than this, because what's going to happen is in those problems, the first step is already going to be done for you. So you run across a problem like this, and it would say something like, solve x equal y plus 2, x plus y equal 4, something like that, right? Now, I mean, a problem like this, all you have to do is take the top equation and plug it into the bottom one. See, so the problem that I gave you required you to do step 1, which is to pick one equation and solve for one variable. But then for a lot of the problems, you're going to notice that that step has already been done. So all you have to do is start from step 2. Pick the top equation or wherever the equation that looks nicer and more convenient, the one that has something solved for. Pick that equation and plug it into the other one. And then you immediately you get your answer, right?
So do you
Because,
suggest us doing, just going step 1 through all the steps?
come again?
Do you suggest us just completing all the steps, even though we don't have, the first one is done for us?
Well, you cannot do step 1 in this case because it's already been done for you.
Okay,
Yeah, so there's nothing to do. There's no step 1 here, right? So in this case, I'll just go to the next step and say, plug equation 1 into equation 2. And when I do that, x plus y equal 4 now becomes y plus 2 plus y equal 4, right? Because x is actually y plus 2. So I simply replace this x in the second equation with y plus 2. And then when I do that, I combine my y's and I get 2 plus 2y equal 4. And then I subtract 2 from both sides and I get 2y equal 2. Then I divide both sides by 2 and I get y equal 1. Once I have this y equal 1, I take it and plug it into either equation 1 or equation 2, whichever one I'm in the mood for using. Obviously, you always want to use the easiest one. I would use equation 1 because it looks easier to me. When I plug it in, I have x equal 1 plus 2, x equal 3. So my solution is 3, 1. All right. Substitution. That's the method. Substitution. So the next method we're going to do is elimination. In some textbooks, they call it addition. But I think addition kind of is confusing, right? Because we already know what addition is. So let's just call it elimination. And so here's the trick. Here's the deal. Okay. What just happened? Okay, here's the deal. Let's say I have a system like this. Two x minus y, okay? 2x minus y equal minus 3. I went too far. I went too far. I want to get this stuff. I want to get this stuff closer. Yeah, okay. Okay, so 2x minus y equal minus 3, okay? X plus y is equal, x plus y is equal to minus 3. Let's say we have something like this, okay? Now, elimination involves, as you would imagine, eliminating one of the variables. Why do we want to eliminate one of the variables? Because when we eliminate a variable and we only have one variable left, it's easy to solve, right? I mean, if I told you solve 2x equal 5, I mean, you can just divide both sides by 2. But then if I said solve 2x plus y equal 5, then, you know, you need to figure out a way to get rid of one of the variables, right? So I'm going to inspect all the coefficients. By coefficients, remember, I'm talking about these numbers here. This one, the number here we know is -1. The number here is 1. The number here is 1. I'm inspecting all the coefficients, okay? I need opposite numbers. So if I can get opposite numbers, then half the battle is already won. What do I mean by opposite numbers? I'm looking at the x's and I see a 2 and a 1. Opposite numbers are actually additive inverses is what the technical term for that. So opposite numbers, by that I mean, let's say -5 and 5, -7 and 7, 13 and -13, -1 and 1. Any numbers where the same number but different signs, right? If I can get that, then my step 1 is a piece of cake. So in this problem, we have that because I noticed that there's a -1 here and a +1 here. The moment you get something like that, you're gonna add the two equations to eliminate a variable. So immediately over here, I'm gonna say add equation 1 to equation 2. When I do that, I get 3x, right? I'm adding these two, 3x. When you add these two, you get 0. It cancels out, equal -6. Then I solve for x. X equal -2. And once I have my x, I take it and plug it into either of the two equations, whichever one I want to plug it into, to solve for y. So if I were to plug it into equation 2, then what I would have is x, which is -2, plus y equal -3. Add 2 on both sides, y equal -1. So we just solve the system. X is -2, y is -1. So the whole idea of elimination is to get the numbers, coefficients, the numbers in front of the variables. You need just two of them, either the x's or the y's. You need two of them to become opposites. Sometimes it's already there for you. Sometimes you have to make them look like that. Okay, so let's look at an example where you're not given that, but you can make them look like that. Okay, so here's an example. Solve. Two x plus 3y equal to x plus 2y equal to, let's go back. 2x plus 3y equal to x plus 2y equal 1. Okay. See, I'm making up the problem, so I have to make sure, the answer comes out nice and, a whole number. I mean, you can have fractions as your answers, but I don't want to scare you by doing problems with fractions in them. I don't even think you will see one with fractions in the homework, actually. But you can have answers with fractions, right? So, here we see that we don't have the opposites that we had conveniently had in example 1. I see a 2 and a 1. Remember that the number here is 1. We know that. I see a 2 and a 1, and then I see a 3 and a 2. It's easier for me to make the x's become opposites than it is for me to make the y's. Why do I say that? Because I can do the following. I can multiply the whole of equation 2 by -2. If I were to multiply the whole equation 2 by -2, then it means I would multiply this by -2. I'll multiply this by -2 and multiply this by -2. So let's say multiply equation 2 by -2. That gives me -2x -4y equal -2. Now I'm going to add that to equation 1, right? Because we're trying to manipulate the equation so that they have opposites. And we have achieved that because now I have the opposites that I'm looking for. So sometimes to get the opposite, you have to multiply one equation. The key thing is, don't forget, when you multiply, you have to multiply all three of them, all three terms. First one, second one, third one, by whatever number you need to multiply by to get your opposite, okay? So now I'm going to combine them. These obviously cancel out, and I have negative y equal 0. Negative y is the same as negative 1y. You know that. So if I divide both sides by -1, I get y equal 0. Because 0 divided by any number is equal to 0. Then I take my y equals 0 and plug it into one of the two equations, whichever one I fancy, to solve for x. Obviously, plugging it into equation 2 would be the quickest way to do it. So I'm going to take my y equals 0 and plug it into equation 2. Like this. X plus 2 times 0 equal 1. X equal 1. Because 2 times 0 is 0. So my solution is 1, 0. See, I got my x and my y. 1, 0. That is elimination. Now, it gets even more interesting. You know, we're gonna do, I mean, not today. If I do that today, I think you would probably just fall asleep. We're going to do systems of 3 equations in 3 variables, right? So those ones would look like this. We're going to solve a system like this. X plus 2y minus z equal 4. X minus y plus 2z equals 7. X or 2x plus 3y minus 4z equal 3. Something like this, right? And we're going to solve for x, y, and z. The solution to a system of 3 equations in 3 variables is an ordered triplet, x, y, z. See, if it's just 2, you call it an ordered pair. 3 of them, you call them an ordered triplet. So that would be an ordered triplet that satisfies all 3 equations in the system. We'll do that next time. But I want to show you another example of elimination, which looks different from the first 2 you just saw. Okay. So let's say you want to do a problem like this. Let's say you want to solve a problem like this. 2x plus 3y equal 5. 3x plus 4y equals 7. Now, it's not so convenient because I realize that no matter what I do, I cannot multiply one of the equations by some scalar multiple, by some number, to conveniently get an opposite number that would make everything cancel out smoothly. Okay, so in this case, I'm going to have to get clever and do something else. I'm going to multiply. Well, I've chosen, my pen just fell down. I've chosen to eliminate x. Okay, you can eliminate x or you can eliminate y, whichever one you prefer. I have chosen to eliminate x. So in my attempt to eliminate x, what are the things I could do to get opposite numbers? Well, if I could get the x in equation 1 to become a -6, and then somehow get the x in equation 2 to become a +6, then I've gotten opposites. So what I'm going to say here is I'm going to take equation 1 and multiply it by -3. And then I'm going to take equation 2 and multiply it by 2. That should do the trick. How do I know? Well, I mean, we're going to see, right? When I multiply the first equation by -3, I get -6x, -9y, -15. When I multiply the bottom equation by 3, I get 3x, excuse me, not 3x, let me go back here. I get 6x plus 8y equal 14. Okay, so all of a sudden you can tell that the numbers are opposites, and if the numbers are opposites, then it's a piece of cake, right? Now all you have to do is just get rid of one of them, and you're done. See, so I multiply the top equation by -3. That gave me -6, -9, -15. Multiply the bottom equation by 2, 6, 8, 14. Add the 2. These obviously cancel out. You have -y equal -1. Well, -1y equal -1. Divide both sides by -1. Y is equal to 1. If y is equal to 1, how do I solve for x? Just take my y and plug it into either equation, whichever one I feel like plugging my y into. Okay, so let's say I want to go with equation 2. I mean, it's just my choice. Actually, in this case, neither one is easy to plug into, so it doesn't really matter which one you choose. You're gonna have to do some calculation. So if I plug this into equation 2, I have 3x plus 4 times 1 equals 7. 3x plus 4 equals 7. Subtract 4 from both sides. 3x equal 3. Divide by 3, x equal 1. So we just solved. X is 1, y is 1. So 1, 1. Well, it would help if I actually had a nice handwriting, so I would make it look nice, but yeah, like this. Okay. So that's the solution. Okay. So any question? Let me know if you have any question. Elimination. Substitution, elimination. Let me go to the textbook and see how far we've gotten. Let me see where we've gotten to. And then I'll let you know which homework assignments to do. All right, chapter 9, or module 9, so they call it. Okay. So we just actually did 9.1. Wow, okay. Okay, so I'm gonna do 9.2 next time and 9.3. System of 3. Okay, so you see what I was talking about. A system of 3 equations in 3 variables, right? System of 3 equations in 3 variables. The elimination method, if you remember, I mentioned that they call it addition sometimes. So this is elimination. So in 9.1, we actually did, in 9.1, we did substitution, I believe. That's what they have here. Yes. In 9.1, we did substitution. In 9.2, we're going to do elimination. And then next time, we're going to do 3 equations in 3 variables. Then after that, I'm going to do some word problems, some simple interest problems, some investment problems. Okay. Then we're going to do 9.3. We're going to do matrices, determinants, Cramer's rule. This when stuff, we're going to skip over that. And then finally, we're going to do this. Okay, so probably take another couple of days. I don't think we can finish all this tomorrow. Okay. I mean, on Monday, I don't think we can finish all that on Monday. Anyway, let me click on the homework and see what's going on. So chapter 9 homework. 29. We're going to do, for now, we're going to do 1, 2, 3, 1, 2, 3, 4. Oh, okay, yeah, I forgot to mention that. Okay. So I need to tell you one more thing before we sign off. I forgot to mention it. But you're gonna do numbers 1 through 10, okay, for your homework. Now, the thing I forgot to mention is that the graphical interpretation of a system of linear equations. Okay, so what I mean is, see, if you take a system of linear equations, okay, and graph the system. Let's say I have x plus y equal to, and then I have the other equation in the system as 2x minus y equal 1, okay? The solution to a system of equations is the point of intersection of the graphs of the equations in the system. So I mean, I make it sound like all I'm trying to say is when you graph the two equations in the system, where the two lines intersect, where they meet, it's the solution. So as you can tell, when I hover my mouse over the intersection of the two lines, the blue and the red line, you see that the solution pops up is 1. So that's another way you can find a solution to a system. There are 3 ways you can do it. You can graph, you can use substitution, or you can use elimination, okay? Now, keep that in mind, okay? That the solution is the point of intersection of the graphs. Now, if you look here, you're gonna see this word. You're gonna see this word dependent, independent, and dependent, independent, and inconsistent. So I want to explain these terminologies, okay? When you solve a system and you get a solution, that solution is a unique solution, right? The ones we've done so far, there's only one answer, and that answer is what we solved for. When that happens, we say the system is independent, okay? Now, there are cases where you try to solve and there's no solution. In that case, the system is said to be inconsistent. And then there are cases where you try to solve and you realize there's an infinite number of solutions. In that case, the system is said to be dependent. So unique solution, what we've seen so far, independent. Infinitely many solutions, which I'm going to show you an example of, it means the system is said to be dependent. No solution, which I'm about to show you an example of, in that case, the system is said to be inconsistent. So let me show you the examples that I'm talking about. Homework is numbers 1 through 10. Let's say you try to do a problem like this, okay? So I just need to make one up real quick. Okay, so let's say you try to do a problem like this. 2x plus 3y equal 5. 4x plus 6y equals 7. Okay, so let's say you want to solve this system. So you start by saying, oh, well, you know, I can multiply equation 1 by -2 to get my opposites, right? I multiply equation 1 by -2. If I multiply equation 1 by -2, that does the trick. Takes care of what I need taken care of, right? Because when I multiply equation 1 by -2, I get -4x, -6y equal -10. Then I combine that with equation 2, which is 4x plus 6y equals 7. When you do that, these cancel out, that's 0, that's 0. So 0 equal -3. Whenever you're solving an equation and somewhere along the line in the process of solving the equation, you come up with a statement, it's obviously false. I mean, 0 has never been equal to -3 at any point in history. It will never be equal to -3. 0 is not equal to -3. That's not true. So anytime you come up with a false statement, like 0 equal -3, 5 equals 17, -7 equal 52, anything you know doesn't make sense, it's false. And then you just stop and say there's no solution. If there were a solution, you wouldn't be getting false statements. So there's no solution. When there's no solution, the system is said to be inconsistent. The types of problems that we did where we got a solution is just a solution, one solution, like all the ones we did before. You have a unique solution and the system is said to be independent. So I've shown you independent, unique solution. I've now shown you false statement, no solution, meaning the system is inconsistent. Now I'm going to show you a system that has infinitely many solutions, which is therefore said to be a dependent system. All right. So here's an example. Let's say I have x plus 2y equal 17. And I have 2x plus 4y equal 34. Okay, let's say I want to solve this system. So once again, I recognize that all I have to do is multiply equation 1 by -2. So if I take my -2 multiplied by equation 1, then I'm going to combine it with equation 2. So this -2x, -4y, -34. Okay. Then I have 2x plus 4y equal 34. 0, 0, 0. Everything is 0. 0 equals 0. Whenever you're solving a system and you end up with what we call an identity, you end up with an identity. An identity simply means it's like you're looking in the mirror, right? You're seeing the same thing on both sides of the equal sign. Like 0 equals 0, 5 equals 5, 6 equals 6, 12 equals 12, -7 equals -7, and so on. An identity. Same number on both sides of the equal sign. You stop. And when you stop, you would say the system has, so let's say, identity. Stop and say the system has an infinite number of solutions, right? An infinite number of solutions, which is also expressed as infinitely many solutions. And the system is said to be dependent. So infinitely many solutions, dependent system. Unique solution, independent system. No solution, inconsistent. Okay. All right. So numbers 1 through 10. And give me some feedback when you try to redo the homework, please. So if you don't have any questions, I will see you on Monday. And we did quiz 1 on chapters 5 and 6. Remember, quiz 2 is due on the 24th. I think that's 3 days from now. And that would be on chapters 7 and 8. Okay. All right. Let me know if you have any questions. No? All right. So I will see you on Monday, and I'm gonna send you the recording to the class. Okay. So take care, and I'll see you next week. Have a great weekend.
Thank you.
Bye.
Bye-bye.
Thank you.
You too.
Bye.
All right. Bye-bye. Bye.